I don't want to talk over the music, but this is a game that is probably more important to me than any other. And I only get to share it with you for 5-10 minutes, now and during the break, so if you're watching, enjoy it. We'll get started in just a bit. Do 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 do. 12:20 already? Oh man. Hold on, let me turn off the sound because I'm just going to leave this in the background here. And we'll go over here. Guess I gotta do my job. Alright, alright, alright. Hi everybody. Welcome to Final Fantasy VI. I mean, Chem 121. So this version of the game came out today. It has been online for 4 hours. So I immediately started playing it. And the music is amazing. But to not get a copyright strike, I have to actually stream the content, I believe. So I'm going to be streaming that during the break, like the actual game, and you could just watch that for a bit. And I'll just leave it on in the background, because whatever. I'm only going to show you like the first 15 minutes or so, so not really big spoilers. But we're going to get started on the lecture, which today is Chapter 8. Chapter 8 uses a lot of the stuff that we talked about yesterday when discussing a property called solubility. This is a trait of matter to mix together two different things. So, for example, water and, say, table salt, or maybe water and vinegar, or water and oil, and why they do or don't mix. So, we're going to talk about that, and it all has to do with intermolecular forces that we talked about yesterday. So, that's going to be super crucial to all of that working out. What else do I want to talk about? Oh, I also want to talk about the lab. So let me get the lab up real quick. I didn't actually pull that aside, but I can do that real quick. This window. This is the window I want. So let me capture that real quick. And we'll just shove this over here and then turn this on. Okay, so let's talk really briefly about lab worksheet number 4. Lab worksheet number 4 is videos, which you can find in the link below where lab worksheet number 4 is. But the gist of the lab is that you're going to be exploring 2 topics that we don't really have time to talk about in this class. One of them we're going to briefly mention in a bit once this loads. You can see it in the back here. So the last thing we talk about in Chapter 8 is osmosis, which is a very important property for how water behaves in cellular membranes and stuff like that. This isn't loading, so let me just open it. Let me get rid of this, and we'll just open the file that I have saved on my computer. And this is going to be similar to lab number 2, where you watch a video or two. Where are they? There they are. And you're going to answer questions about various properties. So let's see if this captures. Window capture. And I want Adobe. There we go. There, that's good enough. Okay. So there's going to be 2 parts to this lab. The first part is the dialysis osmosis part. Dialysis and osmosis are similar things, but they move different substances. Dialysis moves solutes, which we're going to talk about in a second, and osmosis moves water. In most cases, water will be the solvent. And the gist behind both of them is the same. Short version, where there's less of the stuff, your substance moves towards that. Kind of like if I mix, like if I put a drop of food coloring, there's lots of food coloring where the drop is, but there's less of it in the water, so the food coloring moves into the water. Likewise, for the water, there's less water in the food coloring itself, because it's all food coloring, right? So the water's going to move into the food coloring. Now, osmosis and dialysis require there to be some sort of semi-permeable barrier in between them. And it's going to inhibit the flow, but not completely stop it. That's the gist of this section. You're going to explore these properties by watching a video. And I have some information and background that you should read through to explain that. And then you're going to watch a video of an experiment that is done using what's called a dialysis bag. And you're going to see that various properties of it change, such as the color, the weight, depending on what stuff we're putting in there. And there are some experiments that are explained in the video involving an iodine potassium iodide solution and starch, which react together to make a very deep blue solution. So you're going to watch those videos and answer these 11 questions about it. The second part is nuclear chemistry, which is important if you're going to go into like something like radiology. Nuclear chemistry is chapter 11 in this class. We never have enough time to go over chapter 11, and there are very basic questions about it that are asked in this lab, so that you just at least get exposed to it. Not like radiation exposed, but more like just conceptually exposed to it. So I explain a little bit about various properties in nuclear chem. The primary objective of the lab is to understand these 3 types of radiation, alpha, beta, and gamma, and their not their physiological effects, but their physical effects in terms of like what can they pass through. For instance, alpha radiation can be deflected and stopped by very small barriers, such as like a sheet of paper. Beta radiation is much more difficult to stop, and then gamma radiation is extremely difficult to stop. And you're going to see all of these effects on a video, and then you're going to answer some questions about it. So I have some examples of radiation here and how much dosage you were exposed to. Radiation is all around you. It's not something that you should be terrified of, because if you go outside, you're being exposed to cosmic radiation, and you are getting a dose of radiation. You get more of that if you fly. You get that if you get a dental x-ray. All sorts of stuff causes radiation exposure. And you don't need to worry about this because the amount that you were exposed to at any given time is what's considered a safe limit, i.e., this won't hurt you long term. You can go outside all you want, And it's more concerning that you would get a sunburn than that you would get radiation exposure that would cause cancer or something like that. That being said, getting too much exposure to the sun can cause skin cancer, but for different reasons. It's not from these types of radiation that I'm talking about. We talk about half-life. Half-life is how long a sample remains as what it is before irradiating away to something else. The time listed is how long it takes half of a sample. So, for example, if I gave you 10 grams of iodine-131, in 8 days, you'd only have 5 of those grams left. The other 5 would have irradiated and emitted those particles and turned into other things. Whereas if I gave you uranium-238, 10 grams of it, 4 billion years later, it would be 5 grams. So some things decay really quickly, some things decay really slowly. I have several videos that I have you watch for this. So the first one talks about various radiation types, and then the second one talks about the concept of half-life by using a bunch of straws and shaking them up in a thing and then pulling out the ones that have flipped on a certain orientation. And you'll notice that in the video, after each shake, a certain number of straws drop out of the reaction, we call it. And so you can explore the concept of half-life there. And then there's a few final questions here. So there's 25 total questions, and each one's worth 1. Answer them to the best of your ability. That's pretty much it. That's lab number 4. Again, those aren't topics that we really talk about in this class, so they're sort of only explored in the lecture. Osmosis Jones, I don't actually know. I've heard of Osmosis Jones. I don't know if I get the reference, though, so I'm not sure if I understand where to go with that. So I apologize. All right, let's get started. So we're going to talk about solubility first. So the first thing that we want to discuss is, what does it mean to be soluble? What happens when you put substances into other substances? For example, if you put salt or sugar in water, you could taste the salt in the water. If you've ever been to the ocean and accidentally tasted the water, you know very much that it is not just water. It is salt water, and it is disgusting. It is extremely salt. When I was a little kid, I went to the ocean with my grandma. We were in Southern California, and I ran down to the ocean, and I was like, "What's the ocean taste like?" Because Granny knew everything, right? And she said, "Why don't you try for yourself?" And so I ran to the ocean, and a wave came in, and I opened my mouth. I was like, "Ah!" And I will never forget that taste. It was so bad. It was extremely bad. So. Solutions obviously have the stuff that is dissolved into them, but you may or may not be able to see it. So in the top example, if you pour salt or sugar into water and you stir really readily, it appears to vanish. Whereas if I put like some sand or mud or silt into water, what ends up happening is that all collects at the bottom. And no amount of shaking is going to cause that to dissolve into the solution. We're going to call something that dissolves into a liquid medium soluble. And we're going to call something that doesn't dissolve. So this would be soluble. This stuff is dissolving away so that you can't see it. Stuff that doesn't dissolve, like this right here. Oh, this color doesn't show up at all. That's okay. We're going to call that insoluble. And I'll just do that. Now, your indication that something is insoluble is that it will be visibly obvious to you. I.e., if you put something in there and it exists as a clump and it sits there at the bottom and no amount of mixing does anything, then it's insoluble. Now, I say bottom, and I refer to that state for solids. Solids will always sink to the bottom because they're more dense than the liquid. If you have an insoluble liquid and its density is lower, it'll sit on the top. So, for example, oil and water are insoluble, but the oil sits on the top of the mixture. What's important is that you have different phases that are visibly apparent in an insoluble mixture. So in here, we would have the aqueous phase, which is where the water is mostly. And down here, we have the more solid or precipitate phase, where we have a bunch of sand and dirt that's just kind of hanging about. So there are two separate phases, and you can see a very obvious distinction between the two. All right. Now, I have a video of this. I mean, if we're going to get multimedia here with me playing Final Fantasy VI, I could also get a video for dissolving stuff. So let's get that on the screen. Oops. Hold on. You can hear the guy talking. We don't need to hear him talking. But I do want to capture this window. There we go. We'll make that a little bigger. So what we got here... you don't need to see my bookmarks. Just random comics that I read. There we go. So what we're going to do here... Actually, I can make this a little bit narrower so I can get more in here. Is we're going to add 3 different liquids here. So I believe that the bottom one is or it's either dichloromethane or carbon tetrachloride, one or the other. The middle one, so that's the bottom one. The middle one's water, and the top one is hexane. These two are insoluble with each other, and this one is insoluble with the top one. So we have 3 distinct layers, kind of like that density column that we did way back earlier on in the quarter. And what he's going to do, after he's finished adding the hexane here, he's going to add iodine. Iodine is only soluble in things that are similar in intermolecular forces to iodine. Iodine turns out totally nonpolar. It's 2 I atoms bonded together. So it's only going to dissolve in things that are nonpolar. Water, as we discussed yesterday, very polar. Hexane and dichloromethane or carbon tetrachloride, again, I don't remember which one, very nonpolar. And so you could see that as he adds this, the solution starts to turn purple, because the iodine is mixing and dissolving in it. But when he drops the iodine down into the water layer, you're going to notice something happens. So there it goes, and then he's going to drop this down. Now he's going to push it into the water layer. And you notice that it goes right through it, totally uninterested. But as soon as it hits the carbon dichloromethane layer, it starts dissolving immediately. Now, the next thing that he's going to do is he's going to take this bottle, and from the color of the bottle, I have no idea what he uses this bottle for. But he's going to pour all of these 3 things in here. Probably use the funnel, dude. Yeah, good idea. So now he's going to pour everything in here. Oops. A little spill there. That's okay. And then what's going to happen is he's going to shake the bottle really well. Like, it looks like there's only 1 layer in the container, right? He's going to ensure that, at least for the time being, there's only 1 layer. So we're going to mix, mix, mix. And then we're going to pour it back in the container here. And we're going to see what happens. Now, you can tell at the very bottom, something is happening, right? What liquid do you think that is separating out from the remaining stuff? You can type your answer in the chat. I don't know how long this video goes, but... So even though we have mixed it very well, and for a very short amount of time, it stayed 1 phase, all of the molecules of one of the liquids are shuttling themselves in that direction. And there's a very specific reason for that, which that's the whole point of today's lecture, is to talk about this. So, and it is water, very good. Then that checks out because the iodine mixed in the other 2 things, so those 2 things must mix with each other. But the water was keeping them separated before. Now that we've mixed it all together, the water isn't in the way, so to speak. And so those 2 other liquids can get together, the hexane and the dichloromethane. And the water remains on its own and it just shuttles to the bottom. So our goal is to explain why this is today. That's our objective, is to explain all of those things. Now, in order to do that, we have to actually define what solutions are. So, To define a solution, we are going to ascribe the following properties. A solution is any mixture that has two components in it. Those two components will be something you dissolve and then something you are dissolving it into. And on my little cartoon here, you can see that the solute is what you dissolve. You put the solute into the solvent. Now, strictly speaking, by definition, there must be more solvent. And the reason that we ascribe that definition is there must be more of the solvent because otherwise you can't dissolve all the solute. You wouldn't get a solution. What you'd get is a mess. For example, if I had a small amount of table salt mixed with water, it would dissolve. But if I mixed a small amount of water with a heap of table salt, part of it just gets mushy, and I wouldn't have a solution. I would just have mushy salt. So the solvent is the thing that there is more of, but it's also the thing you put stuff into. For our purposes in this class, the solvent is almost universally going to be water. However, solutions are just a definition sort of concept. So all solutions are going to be mixtures, but they don't have to involve just liquids. In fact, on this slide here, I have various amounts or various phases of different substances that mix together. Does solvent greater than solute by weight or volume? It's mass. So we're going to strictly use mass as our definition. However, volume is a useful property to use. But given that density is different for different substances, it's going to matter how we define it. And later on in the chapter, we're going to define solutions in different ways. For our purposes here, let's just stick to mass. But later on, when we get to volume percent, and mass volume percent and stuff like that, we'll calculate them based on whatever property it is that we care about. For instance, a saline solution is mass volume, where you add a certain mass of salt to get a certain volume of saline solution. And then you administer that via, say, IV. So if you're a nurse, this is where it all starts to become relevant and it all starts to come together. I'm going to teach you how to make an IV bag in Chapter 8, which is probably the most practical thing that I teach in this class. Down here on the table, just various examples of solutions. Air that you are breathing is a solution. The solute in air would be oxygen or water vapor or carbon dioxide or whatever there's less of. The solvent is the thing there's the most of, which would be nitrogen. Most of the air you breathe is nitrogen, which is inert and doesn't do anything to you, so you just exhale it. Likewise, you could have gaseous solutes in water. For example, my polar seltzer that I've almost drank all of, because I was too busy playing Final Fantasy VI instead of going to refill my water. I'll go do that during an exam. You guys doing a practice problem or something. And then so on and so forth. Solids are actually very interesting solutions down here. So for example, if I have two solids mixed together, I make a solution. And another term for this, which we also called this earlier on in the quarter, this is called an alloy. An alloy is a solution of metals. So, for instance, steel is a solution where the principal substance that's in there, the solvent, is iron. And then we disperse other solutes into it, such as like carbon or manganese or nickel or I said carbon, chromium or whatever to get that. For our purposes, these are going to be the major ones that we care about, is these right here. All right. Now, like we said before, most of the solutions that we're going to use are aqueous in nature, which means that water is the solvent. Now, non-aqueous solutions do exist and are sometimes important for things like medicine. So some stuff isn't soluble in water, and it makes it hard to administer. So we dissolve it in something like ethanol. So, for example, I want to think of things like NyQuil or Robitussin or whatever. Using ethanol helps the stuff dissolve. It's not pure ethanol. I sure hope not, anyway, because I was given NyQuil as a kid, and if it was pure ethanol, then maybe I understand why I was given it and why I always spit it out. I don't know if you were a kid and you were given NyQuil, but whenever my parents gave it to me, I would hold it in my mouth, and when they weren't looking, I'd run to the bathroom and spit it out because it tasted so bad. All right. Now, this first section is going to talk about various different things that we can do involving solubility. We're going to start with how much. How much can you dissolve? Because there's obviously a limit, right? You can't just put salt into water forever. To empty the entire Morton's can into a glass of water. Like, at some point, it's going to stop dissolving, right? So if you put all of the solute that can dissolve in a solution into a container and then keep going, what ends up happening is you have undissolved stuff at the bottom. We're going to call the liquid layer up here saturated. A saturated solution has the maximum amount of stuff that it can hold. That is, we cannot dissolve any more. It is not possible. It is holding its limit. Now, we're going to get to this on the next slide. But what we have in our solution and what is able to dissolve depends on both the solvent, which in this case is going to be water for our examples, but also its temperature. Temperature is incredibly relevant. The higher the temperature or the lower the temperature, the more or less soluble something is. And it depends on what the substance is that you're dissolving. Most things are more soluble at higher temperature. Now, if you don't have undissolved stuff at the bottom, then the solution is unsaturated, which means that you can hold more potentially. So, unsaturated solutions will have some stuff dissolved in them, but there is no undissolved solute. Now, comparatively, you can look at the two solutions and say, oh, well, this one's unsaturated because it's not as dark. So the top solution is much, much more intensely blue. And that checks out because the more stuff that's in there, the more that dissolves, and the more you would see it in the aqueous phase if it had a color to it. Some solutes are clear or colorless, and thus when you mix them, like table salt is colorless when dissolved. So you don't see any impact on the solution. But this copper sulfate that we're mixing here is very, very deep blue. All right, so those are our two states. Saturated, which has the maximum dissolved. Unsaturated, which has less than the maximum. Now, because there is a maximum, and that maximum depends on temperature, you can plot that information on a graph. And so we've done that here. So here are various substances. And on the y-axis, I have plotted the amount of salt that you can put into this container that holds 100 grams of water. And then on the x-axis, I plotted the temperature at which you reach saturation. So for instance, at 20 degrees Celsius, I can dissolve 35 grams or so of sodium chloride in 100 grams of water. But if I heat that up to 100 degrees Celsius, I can dissolve 40. So I can dissolve just a little more. Other substances become much more soluble at high temperatures, whereas that cerium sulfate that I have down at the bottom becomes less soluble, and that's for thermodynamics reasons that we'll discuss never, actually. That's not this class, that's Chem 162, so if you change your major and want to become an engineer, because chemistry is so fun, and you go and take 161 and 162, we'll talk about it then. What determines the amount of solute a solvent can hold? That's going to be intermolecular forces, like hydrogen bonding or dipole-dipole or whatever that we talked about yesterday. But also the size of the particles and various other factors that we don't really talk about in this class, because they tend towards thermodynamics. So things like if you can dissolve a lot of particles, usually that's favorable. But if you hydrate something with water and it becomes endothermic, that becomes unfavorable. Stuff like that. Or if it's exothermic, it becomes unfavorable. I have to sit and think about it because I'm not in the right mindset to say, okay, well, if I add water and it heats up, okay, yeah, so it'd be exothermic. So my prediction is that this one down here, when you add this to water, it would get very, 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 very hot. And if it was already hot, that energy would not be released as readily, and so it'd be less soluble. We're going to talk about why that works in the next chapter when we talk about Le Chatelier's principle and equilibrium. Now, these numbers represent maximums that you can dissolve, but an interesting thing happens if we do a sort of like conceptual experiment with something that has a very high solubility at a high temperature and a very low solubility at a low temperature. And so here's what we're going to do. I'm going to start at 20 degrees Celsius, and I'm going to look at KNO3. At 20 degrees Celsius, I should be able to dissolve 30 grams. But at 50 degrees Celsius, I should be able to dissolve almost 90. So here's what I'm going to do. I'm going to do these three things in this order. Step 1, I'm going to heat the water to about 50, not negative, but about 50 degrees Celsius. And then step 2, I'm going to add about 90 grams of KNO3. And so I should have a saturated solution, but I want it to just barely be unsaturated. In other words, I'm not going to have any solid that is undissolved. So I'm going to add lots, but not enough to start having a solid crash out on the bottom of the solution that is undissolved. And I'm doing this for a very specific reason. And then step 3 is I'm going to let the solution cool to room temperature. And something interesting happens in that case. And so I'm going to leave that on the screen for just a second more so that you can read it if you want to. But let's talk about what happens and how things dissolve and undissolve at the molecular or atomic level or ionic level, I guess we should say. So on the slide, I have the description of what's happening. But what we're going to do is we're going to go over here. We're going to draw a picture. All right. So here's my container. And here's my solid. I'm going to just draw my solid as a bunch of like little chunks here. And then here's my water. When this dissolves, what ends up happening is the pieces become independent and float around, surrounded by water, right? Now, these pieces can move however they want to in the solution. However, one other possibility that they can do is they can move and bonk back into the solid that they dissolved off of and recombine. So these arrows that represent stuff falling off represent dissolving. But these arrows right here that represent stuff bouncing back around and then landing back on the solid represent recrystallizing. Which is the opposite of dissolving. So what's really happening here is that when my solution has the maximum amount of stuff up in the top, the liquid phase, as it can, at some point I am losing stuff as fast as it is coming back and recrystallizing. And that's when you reach saturation. So saturation is when the rate of dissolving, we'll say speed, equals the speed at which it recrystallizes. Early on, stuff dissolves really quickly, and it doesn't recrystallize fast at all because there's nothing in the liquid phase to recrystallize, right? It's all in the solid phase. But then, slowly over time, the amount of recrystallizing that is occurring matches that of the dissolving speed. And when those two are equal, you've reached saturation. You can't dissolve anymore because it's just recrystallizing as fast as you're dissolving it. Now, what happens if I put in a solution and everything is dissolved and there's no solid down here at all? If this happens, there's no place to recrystallize, right? And if it doesn't recrystallize, then no solid would form. So in our example over here, actually, let me go back to this previous slide here. In this example here, I have created an unsaturated solution, so there's no solid present. And then I've made the solution cool down. So it should hold a lot less stuff in it. But because there's no place for stuff to recrystallize, because I didn't have a saturated solution, it can't undissolve. It can't recrystallize at all. And we get a very interesting state called the supersaturated state. And this is difficult to do. A supersaturated solution requires that you do this very specific order that we just talked about. Heat up your solvent, add enough stuff so that it's still unsaturated, but it is more than saturated than it would be at a different temperature, and then cool it to that temperature. And if you allow it to do this, this is what happens when you do so. I'm trying to pause the video so it doesn't play on its own here. Okay, here we go. Let me make this smaller so that I can embiggen it. Embiggen. There we go. All right, so this is a supersaturated solution of sodium acetate. And when I hit this button and I disturb it or drop something into it, this happens. So the instant that I provide a location for crystallization to occur, it does so. Let me see if I can find the other video that I like to show for this. Yeah, here we go. I like this one better because you can actually see the scientist's reflection in the vial. And so he's going to put a small sample of sodium acetate as a crystallization site. And you can see it immediately start to crystallize. It even falls off of the spatula for a second there. So you see this experiment on YouTube a lot called hot ice, because it looks like ice, but it's also very, very, very exothermic when it's crystallizing. It's releasing energy very rapidly. And then there's one more experiment. There it is. Fun with sodium acetate. That I love to show people. Because this is just it taken to a goofy extreme. And this is a very common experiment that schools have kids do. Because it's just fun. So we've provided a solid for the crystallization to start on. It doesn't always happen right away, which is why it took a second there. Any solid surface will do, but for particular glassware, like a beaker, it's oftentimes too smooth to create a crystallization site. So adding some solid in there or scratching the beaker can actually cause crystallization to occur. Now, this stuff is so supersaturated that it crystallizes instantly, and it expands to a density way, way less than the water. So you pour a few drops on there, and it looks like it's like there's no way you've poured that much stuff, right? It just looks so much comparatively. Now, if you're not careful, this happens. And then I don't know what you do. Like, how do you fix this? You don't. So these are supersaturated solutions, and they're just fun. So I like to show them. Oh, you missed one. There you go. The end. All right. I've shown that video 373,000 times to my students, it looks like. All right. Now, there are other different things that affect solubility besides temperature. If something is a gas and you try and dissolve it into a liquid, the amount of pressure that you have also matters a lot. On the screen, you can see that I have a soda can here. There is soda in the gas phase above the headspace of the liquid, and that forces it to be dissolved into the solution. So the higher the pressure is in your soda can, the more carbonation dissolves into it if the gas is CO2. So this is something you can check out very easily with any carbonated beverage that you might have. So if you buy like a 2-liter bottle of, say, Pepsi or Coca-Cola or whatever, when you hold the bottle, if you like try and compress the bottle with your hands, there's like zero give to it at all, right? It's very rigid. And the reason for that is because the gas inside is pressurized to about 3 atmospheres or so, I believe. That pressure causes the CO2 to stay dissolved in the liquid and give you the taste that you want, because the dissolved CO2 becomes carbonic acid, which gives you the tangy taste of soda that we enjoy. This is why you drink seltzer water instead of just regular water, if you like the tangy taste of carbonic acid. Now, when you open the container, you probably know that sound that it's going to make. It makes a psst sound, right? That's because the pressure inside the bottle is way higher than the pressure outside of the bottle. There's 3 atmospheres of pressure inside, but only 1 outside. And so the CO2 comes out. When the CO2 comes out, there's not as much CO2 holding the molecules inside anymore, because the pressure is reduced, right? So all the CO2 that's dissolved in here slowly dissolves out of the solution, and your CO2, or not your CO2, your soda becomes more flat. So when you've opened a soda or when you've poured a soda, you've probably noticed that all the bubbles try to bubble out, but it takes time, right? And so you drink it and you enjoy it while the CO2 is still in the liquid. Now, when you close the container, you aren't sealing it back in there with all the CO2 that was there before. And so what ends up happening, if we draw our container here, is I have some CO2 that's in here, but less than there was before. And that starts to bubble out to fill this up. And so then I fill this with CO2, which pressurizes, and I eventually hit an equilibrium. But each time I open this, that CO2 escapes. And so it goes again. And so you are slowly losing CO2 every time you open the soda bottle. And the solution inside your soda gets flatter and flatter and flatter each time you open the container. Eventually, it becomes so flat that it's basically just colored water at that point, right? It's water with sugar dissolved in it and caramel coloring to make it look like Pepsi. At that point, we generally throw it away because we call it flat. We don't like it. It's not as good at that point. Or maybe you really like flat soda. I'm not judging you to your face, but okay, I am judging you. So that's solubility and pressure. When you put lots of gas inside a container, it will dissolve. The higher the pressure you put, the more dissolves. When you open a container, that gas escapes, and there is less dissolved as a result. Now, what about temperature with gases? Do I do temperature with gases? Hold on. I might not have that slide in here. Let me see. It doesn't look like I do. How does temperature affect gases? Well, temperature makes gases move faster, right? We talked about this with the kinetic theory of matter at the beginning of chapter 7. Temperature is the speed limit of particles. Gas particles, even if they're dissolved in water, have a velocity. They bounce around. What ends up happening if you heat up your solution is that the gas particles will move faster and they escape more easily. And so there will be less dissolved in the liquid. So for gases, the higher the temperature is, the lower the solubility of the gas. This is why warming of climate is dangerous to many organisms, particularly marine organisms. In water, oxygen is dissolved. Not much, but there's a little. And because the temperature of the water affects how much gas is dissolved, fish prefer locations that are very, very cold. The reason they do is because there's the most oxygen there. Now, if the water is to heat up, then the oxygen is undissolved. It bubbles out of the stuff, and our fish would get sluggish and would eventually die because they would asphyxiate. They don't have any oxygen. So climate change is a particular concern with regards to solubility because as temperature increases, gas solubility decreases. And at some point, if you heat up a solution too much, the amount of dissolved gases, in this case oxygen, is too low to support life. Do gases have a boiling point? They do, but it's below whatever temperature you're at. So, for example, carbon dioxide's boiling point is well below room temperature because it's currently a gas at room temperature. Gases are just liquids that have already boiled, basically, right? There's a cat right here that wants attention, but I have to keep teaching. No, I know you're soft and pretty and friendly. He's going to jump in my lap, and I'm going to have to push him away. But I'm just petting him here. All right. On the screen, you can see how solids dissolve. The way that this works is that here are my water molecules. Water molecules are going to interact with my solids and cart away the ions, as you can see here. Once all of the ions have been carted away to be individual ions just surrounded by water molecules, then we consider the solution dissolved, and this would be unsaturated because there's no solid remaining. Now, all these ions are still there. Again, you could taste salt water if you sip it. Don't go to the ocean and sip it like Childhood West did. That's a bad plan. I believe, yeah, here's a zoomed-in case of this. Now, because sodium is positive and chlorine is negative, I'm just going to highlight these a little more obviously. And water is polar. What water does is it aligns itself so that the opposite charge aligns with the ion it's interacting with. So we know that water looks like this. Here's H2O. And we know that this side is delta positive and this side is delta negative. And it has a permanent dipole interaction. And so what water does is it aligns the appropriate charge with the ion. For the positive ion, it would align the oxygen side because that's delta negative. For the negative ion, it would align the positive side, which is the hydrogen end, because that's the delta positive side. And the interaction of all of these surrounding each ion is enough to cause the solution to dissolve. This specifically is called hydration when water is the solvent. For other solvents, we call it solvations. Now, this interaction is called an ion dipole force because we have an ion and a dipole that interact. And you could just think of this as an intermolecular force that's better than regular intermolecular forces that we discussed. It's sort of the between state of ionic bonding and dipole-dipole. So now that we know how solutions form, we can predict what solutions will form in a mixture. The general rule that we follow and that we'll follow for this class is like dissolves like. And what we're referring to is polarity, more or less. Excuse me. Think of polarity as like a small magnetic force. We were using this analogy all day yesterday, the magnet on the fridge analogy. Things that are polar are like miniature magnets. They attract to other things that also have that potential to be attracted to or attract other things to themselves. So something that is polar will stick to other things that are polar because they all have dipoles, and so they can arrange themselves as such. All the positive dipoles can align with all the negative ones, and then they can stick together. Things that are nonpolar have only dispersion forces, and so they'll stick to anything with dispersion forces, but given the option for two things that are polar and nonpolar to interact, only the polar ones will stick to themselves, and all the other ones get excluded. And so the reason for this is because of those attractive forces. Because dipole forces are so strong, compared to London dispersion forces, all of the dipoles will stick together like magnets. If you have a bag full of magnetic marbles, and you put in glass marbles and you shake it up, you end up with a clump of magnetic marbles, and all the glass marbles are excluded from that. And the reason for that is because the magnets hold all the other magnetic things together. The non-magnetic ones just get discarded. They get pushed aside. In solutions, it's the same thing. Whoever is the strongest intermolecular forces is the winner, and those all cluster together. This is why the water clumped together and separated from the dichloromethane and the hexane in the first video we saw, and then just sunk to the bottom. The other stuff was excluded. They didn't particularly stick to each other. That's just where they happened to end up. So you can think of anything that just has dispersion forces as sort of like the discard. It's where all of the other stuff ends up. All the polar stuff will then stick together. All right. When we come back from the break, we're going to look at this chart and do some practice problems. But first, I need to go get some water real quick. So I'm going to do that. I'm going to put this back on the screen. Or I'll put this on the screen. So let me put a timer up here. And then I'm going to move the timer. Oops, I don't want to do that. Down here. Oops, I don't want to. Because now I can go back to this. And do that. All right. So I'm going to go get some water. And then I'll start the timer. So we'll take a slightly more than 10-minute break. So I'll be right back. Alright, I'm going to start the break timer here. And kick back and relax for 10 minutes and enjoy the introduction to Final Fantasy VI, where we start by fighting for the bad guys. Mysterious woman and 2 Imperial soldiers out to do something nefarious, I'm sure. Oh, I'm out of time, so hold on just a second. I guess that's where we will leave that. Hold on, let me turn off the music again. There we go. Hopefully you enjoyed that. If any of the story looks compelling or interesting in any way, like, I cannot implore enough to play Final Fantasy VI. It is such a good game. Alright, so back to this. On the chart here on the screen, I have a list of some common substances and whether or not they dissolve in water. Now, solubility is very, very complicated because there are a lot of factors that we haven't really gone over because they're too complex for this class. So, like things like thermodynamics and so on and so forth. So what these charts attempt to do is summarize common observations of things that always seem to dissolve or things that always seem to not dissolve. So the way that we're going to use this chart is in the following manner. So there are two sections to the chart. There's the soluble section and the insoluble section. What you're going to do is you're going to look for something that is in your compound in the charts on the side on the left. And then what you're going to do is you're going to look for an exception for whatever else it's paired with. So for instance, if I grabbed, say, NaCl, we know that sodium chloride dissolves in water, right? So I would look for one of these things in the left column. And so sodium appears right here, and so does chloride. Usually you're only going to find one of these things in your chart. I just happened to pick one that had two. And then we would say, okay, sodium is soluble No exceptions. Everything containing sodium as an ion is soluble in water. Or you could say chlorine is soluble. Oops, I went way too far down. Unless it's paired with one of these things. And then we would check them. Well, I have sodium, so sodium is not any of these. So therefore, we would conclude soluble. Okay, so that's how we use the chart. Let's do another one real quick. So let's do, we'll say aluminum carbonate. Is aluminum carbonate soluble or insoluble? So I got to look for one of these things. So here's carbonate. It shows up in the chart. Carbonates are insoluble unless they are paired with group 1A or ammonium. We don't have that, so this would be insoluble. However, if I instead looked at potassium carbonate, we would do the same process and go, okay, carbonate insoluble unless, oh, wait a second, potassium is a group 1A element, and so then we would say soluble after all. So that's how you use this chart. Now, the problem with having a chart on this slide is that when I go to other slides, you can't really use the damn chart, right? So what I want you to do is I want you to try and predict which substances will be soluble in water. Now, down at the bottom, I have a few other things that are mixed together, and I want you to try and predict those based on like dissolves like. And so what I'll tell you, I'm going to write down, so we know that water is polar. And I'm just going to write down the polarity on all of these. There you go. So go ahead and do that. Refer back to the chart if you need it. What I'm going to try and do is I'm going to put this on the screen for like 5 seconds. So look at whatever the timestamp is here so you can go back to it. And then write down these questions here, and then you can refer back to it. If somebody asks me to go back to the previous slide, I will also do that. So just let me know, okay? I'm going to give you about 4 or 5 minutes to try these, and then we'll go over the answers in a bit. See you soon. All right, one more minute. We'll go over the answers here. All right, let's go over the results here. So, let's go back to the previous slide. So we're going to do sodium nitrate first. And let's find something in here. So I'm going to just pick nitrate, although you could have picked sodium right here. Nitrates are soluble, no exceptions. So sodium nitrate is soluble. We'll write that down. All right, let's go back and do silver chloride. So we'll clear all. So we'll look on our chart. The first thing that I find is chloride. I think it's the only thing I can find. Chlorides are all soluble, unless you're paired with silver. So we would include we would conclude insoluble. Oh my goodness, I have a frog in my throat now. There we go. How about calcium sulfide? Calcium sulfide. So let's clear all. Calcium sulfide. So we're looking on the list here. Sulfide. There we go. Okay. So sulfides are insoluble unless you have... Oh, there it is. Calcium. So we would say soluble. So calcium sulfide should be soluble. And it is. And then for these next ones, it's just like dissolves like. Are they a similar polarity? If they're polar, they'll dissolve in each other. If they're non-polar, they'll dissolve in each other. But if they're one or the other, or one and the other, they don't. So this pair will be soluble. And so will this pair. But this pair will not. Because I have a non-polar and a polar. So water and octane do not mix together. You get two separate layers. This is why you can't put water in your fuel tank. If you do, your engine just dies because it tries to combust the water. And water is the product of combustion, so it is not going to happen. All right, and there's the homework practice at the bottom. So let me know if you have any questions about solubility. All right. We've done all this conceptual work. Now what we're going to do is we're going to assign numbers to it. Don't worry, we're going to do very basic math here. We're going to give 3 formulas. Really, the trick to this section is just trying to keep the formulas separate. 2 of them are going to look the same, and then the third one is going to be very, very different. So here's the first means by which we're going to figure out the amount of solute in a solution. And this is called percent by mass. What we do is we weigh the solute, and then we weigh the total solution when you're done, and then take a ratio. Now, it's important to note that the solution is both things put together, right? So that means that you don't want to measure them independently. You want to measure them at the end. Now, with mass, it doesn't matter, but with volume, it does matter. With masses, you could just say, oh, this one weighs 5, this one weighs 10, the total should be 15, right? But the practice to get into is just measure it once you've mixed it, right? Another reason that you'd want to do it that way is that if you measure 5 grams of solute in a container and then you transfer it, you may not get all 5 of those grams in, right? Some of it might be stuck to the container itself. You might only get 4.99 or something. And that could matter. So measure the mass of the solution once you've made the solution, and you'll be in good shape. All right, let's do an example of this. I'm going to put 5 grams of sodium hydroxide in 100 grams of water. I want you to tell me the mass percentage of the solution. Hint, it is not 5%. If you get 5%, you've made a mistake. So try this calculation. I'm going to hit mute. I'm going to give you a few minutes to do it, and I'm going to write the formula for percent by mass on the screen here. So good luck. We're all counting on you. All right, one more minute, and we'll go over the answer. Once you got an answer, type it in the chat for me. All right. So let's go over the solution here. So in order to calculate this, we need the mass of the solute. So that's pretty straightforward. It's 5 grams. Then we need the mass of the solution. Well, the mass of the solution is the solute plus the solvent, right? So that would be this, 105 grams times 100%. So we get 5 divided by 105, which is actually slightly less than 5%. And I get 4.762%. Now, because this was a mass percentage, the way that we indicate that is by writing MM. You may also see WW for weight. Either of those is okay. All right. Let's do another one. This one is percent volume. It is literally the same thing as the percent by mass formula, but it uses volume instead. And so all we do is adjust the formula to, boop, there we go. Specifically for this, you can use any volume you want. I'm going to recommend milliliters for the next example, because that one has to be in milliliters, and if you just do everything in milliliters, it's fine. But there is a major, major catch here, and that is this part right here. Remember how before I said, oh, to get the volume, or I'm sorry, to get the mass of the solution, you just add the solute and the solvent together, right? But if you try and do that with volume, it doesn't work. If you add two volumes together, you don't get what should be the sum. So 50 milliliters of water and 50 milliliters of ethanol is not 100 milliliters. And this is not intuitive. Why would volume be like this? I'm going to show you a picture, and it's all going to make sense. If you fill a jar with golf balls, and you say, oh, the jar is full, I can't put any more golf balls in there, and then you proceed to add something that's smaller than golf balls and it fills in all the crevices, you're filling in more of that space, but you would still say the container is full, right? Molecules do the same thing. When molecules mix together, the smaller molecules will fill in the spaces between the bigger ones. Maybe not to this, like, egregious of a degree. Like, this is a very exaggerated picture that we're using for here. But it does happen somewhat, and the result is that the volume does not change as much as you would expect it to. And so I have a video of this too, which I love this video because it's very, very apparent that, like, wow, these don't add together at all. It's not even close. So let's bring that up on the screen here. I don't want the solubility of iodine. I want volumes don't add. There we go. Let me hit play here. And then we'll fiddle. Oh, this is fine. Okay, cool. All right. Got to cover the chat for just a second. All right, this guy is Gross. Literally, that's his name, George Gross. I make that joke every quarter, right? And I always feel bad about it. And George here is an instructor. I don't actually know where he is. He might just work for Flint Scientific. I might be getting my instructors mixed up. But what George is going to do here is he's going to mix these two solutions. One of them is water and the other one is ethanol. And he has color-coded them with a dye. And he's going to add the remainder of the solution to the container so that you can see that he is adding the volumes that are indicated. So on each volumetric flask here is a line. When you add the solution up so that it touches the top of the line, you have reached the volume stated on the flask. So this would be 500 milliliters for each of these. And then we have a 1,000 milliliter flask that we're going to put both of them into. So I'm going to just fast forward through this a little bit because he takes his time. He's doing it very carefully because we want to be precise here. Okay, there we go. Now he's going to do the same thing with the ethanol, and we'll fast forward through that too. There we go. That one's done. And now we're going to mix the two together. We're going to put them into the big flask. 500 plus 500 equals 1,000, and on the 1,000 milliliter flask there is also a line. that is carefully measured out 1,000 milliliters. So we're going to pour this in here, and it takes a second. Pause. All right. Over here in the flask that he is finished, you can see there's no liquid. So this is not an illusion. This is not a trick of the eye. We're going to pour the next one in. Blue and yellow make green, so the solution should turn green, and it totally does. I can't go that low. And there we go. Pause. And you can tell that there's nothing in this container either. So there's not like a hidden 5 milliliters or something between them. But when we look at the flask here, you could see that he came up well short of where he should be. There's no way we're missing this much liquid in those two vials, right? You could make an argument that, yeah, maybe there's like a drop or two on the sides of the container, but there's no way that there's like this 10 milliliters or so that's missing here. That could even be up to like 25 or even 50. So when volumes are given to you in a problem, you cannot simply just add them together. You have to know the volume of the solution in order to know what to calculate. All right. And so this is why in the previous section I suggested just weigh the solution when you're done. Just get into the practice of observing the finished part if that's what you want to measure, and don't rely on addition or subtraction or whatever. All right. Since volume percentage is the same process as mass percentage, I don't have an example prepared for that. There will probably be one in the Now You Try It in a second here. We're going to move on to mass volume percentage, which uses a different set of units. Importantly, we need to use the following convention. Mass needs to be in grams and volume needs to be in milliliters. This is very specific for mass volume percent. We need to use those specific units, or else this ratio doesn't work as intended. Now again, with the volume of the solution, you need the volume to be measured after you've prepared the solution. Because adding a massive solute to your solution will change its volume. Very little, but it does change it very slightly. So let's do an example of this one. I'm going to prepare a solution with 12 grams of sodium chloride, and I am going to add enough water so that the volume of the solution ends up being 50 milliliters. What is the mass volume percentage of sodium chloride? This one should be pretty straightforward, so I'm going to give you 2 minutes to calculate the answer. Put it in the chat, and we'll go over the answer in just a second. All right, let's go over the solution here. We'll do that on this screen, I think. Because for whatever reason, PowerPoint is very, very sketchy when it comes to like writing on it. And I have no idea why. All right, so we're doing mass volume percentage. And so we do have to put mass in grams and volume in milliliters. So be careful of that. I might give you a problem where it's in like liters or something. So just be mindful of that. Make sure you do the conversion. So I've got 12 grams of sodium chloride divided by 50 milliliters times 100%. Now, you'll notice that these units don't cancel. And where do they end up? Well, if I do 12 divided by 50, I think I get 24, right? Yeah, 0.24 times 100 is 24. So I'm going to write out this. And in the parentheses is where they are implied, but they do just disappear. This is one of these oddities about teaching a lower level class where I don't teach you about dividing by a reference so that the units cancel out. For our purposes, don't worry about the units for mass volume. They get wrapped up into this percent MV, which we indicate at the end. And that'll be good enough. This is an intro chemistry class, so I'm not going to make you worry that much about these specific units, because this is one of the weird cases where we have to do something very technical, and all it does is cancel out the units. So why add extra steps to confuse you guys? So I clicked the wrong thing. There we go. All right. The last way that we're going to learn to express concentration is called molarity. Molarity is defined as this. I said this. There we go. I have it animated incorrectly, I guess. Molarity requires us to know the number of moles of solute. And then we'll divide by the volume of the solution. Note that the volume in this case is in liters. So there's another potential stumbling point, is getting the units mixed up. Now, because it's an online class, you don't have to memorize the formulas. You can always refer to these. But when you are doing your calculation, be very careful that you do not accidentally apply the wrong units, because your answer will be 1,000 times too big or too small, depending on which way you go. All right, let's do an example for molarity. I'm going to make a solution using this many moles in this volume of solution. What is the molarity of the solution? I actually just want to check something really quickly. Do I have a second example in here? I do. Okay. I'll start by letting you try this one. Beware, I have put a little trick in there. So if you get a really tiny number, that's an issue. All right, I'll give you 2 or 3 minutes to try it. We'll go over the answer in just a second. All right, one more minute, we'll go over the answer. All right, so we'll go back over here to nothing. We'll fix that. All right. So, oops, I need to do this to ungrayscale it, which I've learned how to do now. And so we've got molarity, which equals moles of solute over volume of solution in liters. So we'll just put the numbers in here. So 4.35 moles KNO. Oh, not KN. Oh, I thought it was potassium nitrate. It's potassium permanganate. KMNO4 divided by the volume. Now you'll notice that the volume is not in liters, right? So I need to do that conversion first. And then I can add that up here. And when I do that, I get looks like 5.8 0 moles of KMNO4 per liter. Now, this unit right here can be expressed in a shorthand method as just a capital M, and then you write what it is after it. So we have a 5.80 molar solution, or moles per liter. All right, so let's do the same thing again. I'm going to leave this one on the board to guide you here if you'd like. But this time I'm going to give you 20 grams of a solute instead of moles. So you're going to have to figure out how to turn this into the correct units on your own. 20 grams of sodium hydroxide. I add enough water that the total solution volume is 100 milliliters. What is its molarity? Okay. I'll give you a few minutes to try that, and we'll go over the answer. And I think we're done for the day after that because it's already 2:10. So go ahead and do this problem, and we'll go over the results in just a second. All right, one more minute. We'll go over the answer. All right. I'm on the wrong screen, though. Hold on. There we go. All right, so the formula for molarity is the same thing. You'll notice that I'm writing out the formula every time we do this. It's just good practice to do that so that you eventually will memorize it. But if you don't, now you just know, okay, I need to find this thing, and then I need to find this thing. And it gives you a plan, right? All right, so I need the number of moles of solute, but I have the number of grams of sodium hydroxide. Well, if I go over to Lentech, I can find how many grams per mole there are of sodium hydroxide. So let's capture this. Boop. There we go. And we'll type in NaOH. And it says 40 grams per mole. So we'll write that in here. So my units cancel, and in 1 mole there were 40 grams, like Lentech told us. So that means that the number of moles that we are working with is that. How many sig figs should my answer have? Well, this is 3. This is 4. So my answer should have 3. And then what volume do I have here? 100 milliliters. So you can do the calculation to get that to be 0.1 liter. But now we'll just plug all this in. So 0.5 moles of sodium hydroxide over 100 milliliters, which is that. And there's your molarity. All right, and we're all set. All right, and that is all the time that we have for today. So now you've seen how to do a few examples of different concentrations. So what I'm going to do is I'm going to put this on the screen here. So there's our solution. I'm going to put these on the screen here just so the homework practice is at the bottom there. So we're going to start by doing these exercises next week on Monday when we return. It will be week 9. We're going to finish chapter 8 on Monday. Possibly start chapter 9 on Monday as well. We'll probably finish chapter 9 on Tuesday. There may be an extra lecture just to squeeze in enough content. Because I would like to start chapter 10 by... I would like to start chapter 10 on Monday of week 10 at the latest. So we'll see if we need to do that. I will send out an announcement if we need to have a third lecture next week. But otherwise, we're done here. Oh, I can get rid of this. We're done with that. I need my little outro here thing. Gotta do that. I posted quiz 7, I believe. So that should be available. I might not have clicked a button to make it available now that I think about it. But I'll go do that immediately after class is over. But quiz 7 is due next week on Tuesday, which is March 1st. Wow, we're already at March. Holy crap. But otherwise, have a wonderful weekend. That's all I got. Work on that quiz. Work on lab worksheet number 4. Let me know if you have any questions by email or the Discord. And play Final Fantasy VI. It's real good.